Alright, so welcome to Chapter 17, Part 2. Our main focus today is going to be single slit diffraction and circular aperture diffraction. Again, diffraction is just the spreading out of light as it passes through an opening that is smaller or equal to the wavelength of the light that is passing through it. And this word diffraction supports the wave model of light, right? And so last class we talked about how we will send light through double slits and diffraction gratings, which is just lots of slits. And then, well, today we're going to talk about a single slit. And okay, well, what if we, instead of having this kind of rectangular shape, have a circular shape that light passes through? What type of pattern do we see as a result of that? So a single slit diffraction is a little bit different than double slit diffraction. And it's kind of interesting why this happens. So we see that central maxima and then an outer band of m equals 1. With the double slit, though, we saw a lot of these things, and we know that the bright spots are due to constructive interference and the dark spots are due to destructive interference, and that makes sense with double slit or diffraction grating because we've got each slit acting as its own wave, right? And then it makes sense that if I've got two waves that they'll be interfering with each other. But why on earth, if I've only got one slit, right, and if I'm looking at it from above, that looks like this, why do I see that kind of circular arcing afterwards, and then why do I also see this same sign of constructive interference and destructive interference if I've only got one wave? And the reason behind that is Hughes' principle. So if I have a single slit, and this is, again, an extremely small scale for light, but I can imagine each and every point along that acting as its own wave, as if it were emerging from its own slit. And because I've got multiple waves, well, they interfere, right, to produce constructive interference for my central maxima and constructive interference for my outside 2 maxima, and then destructive interference to produce those dark spots, right? And so we can kind of imagine on a micro scale this happening. With single slit, again, here's just kind of a mock-up of that. If we have light of wavelength lambda, slit width of A, right? And remember D from the last one was distance between the slits. Well, we've only got one slit, and so we'll talk about how wide that is with regard to the wavelength. Distance L is how far away the screen is. I would like you to take a second and copy down this diagram. It's a really great representation of the variables that you're going to see in this formula. And we see this new variable P. And I'd like you to look at where P is occurring. So this is the light intensity, this little wavy line. And so high points would be high intensity. Those would be bright spots. But then these P's are marked where the light intensity is 0. And so P is actually dark bands. So up to this point with double slit and diffraction gratings, we've talked about the bright spots and their location. For single slit, we changed to talking about the dark spots and their location. So we've got this new variable P. But it works the same with the exception of the bright spots. We had a central maxima. We begin our P numbering system, dark spot numbering system, with 1 because there is no central 1. We just start with the first one out. Right? All right, and these can go ahead and get added to your formula sheet. And so W tells us the width of the central maxima. And so if I'm looking at this picture, W is how wide that bright spot is. Right? A is the width of the slit. Be sure not to get these two confused along the way. And then remember that P is dark fringes. So we've got the angular distance of P as long with the metric distance of P. All right, and a circular slit is more or less the same thing as a singular slit. However, it's now in the shape of a circle. So we still talk about the dark spots, and we can calculate both their angular distance as well as their geometric distance in terms of y sub p. The only difference here from a single slit is now we don't have A, the width of the slit, we have D, the diameter. And instead of making these rectangular patterns, well, it's going to make this concentric circle pattern. And so we can talk about, again, kind of angular distance about to here for the first one, or the second ring, or the third ring, but differing from double slit and diffraction grating, in that we're talking about the dark spots instead of the bright spots. Right? And these will need to be added to both your notes and your formula sheet as well. I'm going to take a second here to talk about thin film interference, which also supports the wave model of light. We're not going to do any calculations for it, but this is a thing that we do use in daily life for a couple of things. And so thin film interference is when wave interference, and we're going to talk about constructive and destructive, and this is actually kind of a spectrum, right? And so I can get lots of things in between. This happens when light moves through a very thin interface. And so in chapter 18, we talked about light kind of refracting as we go like from air to an aquarium, etc., etc. This is refraction from different media that's occurring on a very small scale and a very thin scale. And this causes something that we call a phase shift in light. And I'll show you a picture of that here in just a second. The most common example, though, that you're familiar with of thin film interference is like oil or soap bubbles or things like that, where you see this kind of rainbow quality. You can usually see it after a good day of rain, which we've had lately. So look around in the parking lots on the ground and you'll see some examples of thin film interference. Right? This is wave interference caused by light. And so as light comes into this thin film from air, just like you saw with your prisms in this large scale, some of that light gets reflected off of, some of that light gets reflected off of the front surface, right? And just goes right back out. But some of that light actually winds up passing through, and there we go, and reflecting off the back surface, and then some light, even still, and I don't have a picture of it, some light, as long as it's not at that critical angle, will continue all the way through that media. But thin film interference happens as light reflects off of this top surface and this back surface of whatever the media is. Usually something thin like soap or glass or a little film on top of something. When it's reflecting off of the front, it comes back, what we say, out of phase. Which is a form of like destructive interference, right? We've got the crest lining up with the trough, and so those things will cancel out. Off of the back surface, there is no phase change. And so what we see is troughs lining up with troughs, and we get constructive interference. As a result of this, the net change in the wave, and kind of depending on the properties of that thin film, how thick it is, the wavelength of light coming in, we can see a couple of things happening. We see some destructive interferences, we see some constructive interferences, and we even see things in between. And so the things in between are what cause those rainbow patterns of the Roy-G-Biv. And we see that repeated over and over, just like you see with raindrops in a rainstorm creating the rainbow because of the angle at which they're refracting that light. So we can use thin film interference to measure the thickness of objects. There are some formulas to do this. However, I don't want to go through the paces of that. I want you guys to master single slit, double slit, and diffraction gratings. However, we do use thin films in our daily life for a few things, right? We use these for optical coatings. So if you have glasses that have a reflective or an anti-reflective coating on them, what that is doing is that's a thin film that's been placed over your glass to kind of dull out the constructive interference off of that back lens. And so we see that as looking like this. Once you put that thin film on, you get that destructive interference. It's kind of the same idea as noise canceling headphones, just with light instead. Right? We do see this in microchips and processors to kind of eliminate static interference. We have protective coatings for materials like your cell phones, And then in nature, this is a natural thing to produce iridescence. And this word iridescence is like a shifting of colors. So bird feathers, we see this a lot, that within the individual hairs of a feather, they're very, very thin, and they get this light interference off the front, light interference off the back, and so that as you change angles, you actually see kind of this rainbow color. We see this in butterfly wings a lot. Their cells are very, very thin on top of that wing to produce iridescence. Peacock feathers are another really good example of thin films in nature, right? In different animals, this is used for different things. It could be to blend in, it could be a mating display, depends on the animal. All right, and with that, your homework. Right, please be sure that you filled out the accompanying notes with this short mini lecture, and I'd like you to go ahead and start these conceptual questions and have them done when you get to class on Monday, and then we'll run into this and do a little bit of test review for your test on Wednesday. Have a great weekend.